So how do covalent bonds form then between these molecules, between atoms? So you have to have a combination of forces that result in the formation of the shared pair of electrons. The electrons of each atom are going to have some conflicting or counterbalancing forces. So each atom will have electrons that are attracted to a nucleus. So they're attracted to their own nuclei, but then they're also attracted to the nucleus of the other atom. In addition, the electrons are going to repel one another between the two atoms. So you have a balancing of forces that have to be put in perspective before you get a situation where there's an actual bond form. So you have to have enough attractions to get them to stay together and not totally repelled from one another. So what happens if you're making a bond between the two atoms can be thought of with this graph. This is a very simplistic molecule where you couldn't have very many more parts, or the simplest number of parts would be 2 hydrogen atoms, 1 proton, 1 electron. And the graph gives you an idea of how much energy there is between the two in the system, depending on how far apart they are. So on the right, when the 2 hydrogen atoms are far apart, attractions are too weak, and there's no bond going to be formed. If instead they are too close together, and this scale is not particularly labeled here for you, but you get the idea. If they're too close together, the strong repulsions between the electron clouds are going to occur. So somewhere, and that's a very high energy situation. This is high up here, and a lower energy situation is somewhere down here. And notice that it's apparently in negative values of energy, but they're not giving you numbers at the moment. And so when they are at appropriate distance, they're optimally separated. The energy is at a minimum, and apparently you get a bond length that's in the picometer range for a pair of hydrogen atoms when they make a covalent bond. So at that place, when it's optimally separated, the balance is appropriate between the attractions and repulsions. When we're talking about these covalent bonds and how they're represented in various compounds, they're going to be shown in a variety of ways. There will be chemical formulas that are very simplistic, that simply represent the numbers and types of atoms. There will be structural formulas, and as the chapter progresses, there will be more conversation about how this is done. But individual lines are representing a shared pair of electrons. And so that is a covalent bond when you see that line in between atoms. Another one there. So there's lots of covalent bonds in this molecule between the carbons and the hydrogens and the oxygen of ethanol. And then on the right is a molecular model. So that's a different way of showing things. Sometimes we'll bring out models. Models are helpful because they give us a way of viewing things that is more three-dimensional at times. And so if you have 2 carbons and oxygen and some hydrogens in that form, we call it ethanol. Again, the covalent bond is represented in this sense by sticks between the atoms, between the spheres. So if you had another molecule, we could represent these in another way. This one's called propane, and you could figure out its formula because you can count up the parts. And apparently we're going to try to do these in an order that carbon tends to end up first and hydrogen's going to be after it. If you count them all up, it looks like 3 carbons and 8 hydrogens, 2 different ways of representing the same compound. And you have to know something about proper arrangements of bonds to know the correct geometry of how these things are aligned. But for the moment, that molecular formula is represented in these 2 other models. Sometimes these models are far more informative and essential because in a molecule like glucose, which has a much more complicated molecular formula, you couldn't begin to guess how the molecule is put together without a lot more information. So the structural formula on the left is quite detailed and hard to read if you don't know what you're looking for. But that's life. We'll get used to these things gradually. And so the structural formula there makes it evident that there's actually a ring in the middle of all of these atoms that's essential to the structure of glucose. The same thing is evident in the ball and stick type model at the right. And, I didn't mention that before, but carbon is going to be black, oxygen is red, and hydrogen is white or gray, however that view looks to you. And so those are common usages for symbols, for ball and stick models, for a variety of things. what one can do if you want to go another step of adventure is to take on a structure and come up with a chemical formula. Well, this is an exercise in counting. And so we'll typically list things with carbon and hydrogen first and other atoms afterwards, but it's not a hard and fast rule about which ones go in what order. So let's just do this order for now. And so for this compound, it's called methionine. It's an amino acid, and it's notable because it has sulfur in it. That's what's unique about it. And so there's 1, 2, 3, 4, 5 carbons, a bunch of hydrogens. Oh, wow, let's see if we can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, if I got it right. Their oxygens are 2, and 1 nitrogen and 1 sulfur. Hopefully you agree. The other molecule on this picture is adrenaline, which has got an awful lot of parts. Again, you'll need to know the color codes to make sense of it. Nitrogen is blue, oxygen is red, hydrogen is that funny gray or white color, and carbon is black. So if we had to put a formula to this, let's see, what do we have? I see 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. And oxygen, or hydrogens, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oxygens, well, there's several in this compound. So oxygen has 1, 2, 3 in that particular structure. And then, of course, there must be a nitrogen in here, which I didn't put in my list yet. Only 1. And so that completes the formula for adrenaline, the molecular formula.